Alright. So based on this mass and stiffness, it will have a natural frequency, that is omega n, and that is given as square root of k by m. Alright. So if the system is allowed to oscillate on its own, this will be the frequency with which it will oscillate. But now in our case, alright, so this is the mass, and to this mass this external force is attached, right? So now, and the frequency of this force is f0 cos omega t. So this f0 is something like this, okay? So it has an amplitude of f0 and it is a cosine wave, okay? Maximum amplitude is f0 and is a cosine wave, and the frequency is omega. Alright. Now, since the mass is attached to this force, the mass now will not oscillate with its natural frequency, but it will oscillate with the frequency of the external force. Alright, and that frequency is called as the forcing frequency. Alright, so there are two things: natural frequency versus and forcing frequency.
Okay, sir. Thank you.
Okay. Alright. Okay, so we'll
Sir,
continue with,
sir,
yes, yes.
uh, and why the word excitation is used? Excitation force.
Because this is the force which is applied, right? So mass initially will be stationary, right? So if you want to move this mass, some external force will be required.
Okay.
Okay, and we are doing forced vibration. We are now studying forced vibration, right? We are not studying free damped vibration. In case of free vibration, what we did, we just gave some displacement and let the mass oscillate on its own. Alright. In this case, the mass is not free to oscillate on its own, but it is forced to oscillate as per the external force, and that is nothing but that is why it is called as the external excitation force.
Okay, sir.
Alright.
Yes, sir. Thank you.
Oh. So we'll continue with the recap. So this was the governing differential equation. We established the governing differential equation. The governing differential equation is linear, second order, and non-homogeneous governing differential equation that gives rise to two-part solution, complementary and particular. The complementary part solution, the solution is similar to that of the free and undamped vibration, free damped vibration. Okay, and this was the solution. So as you can see, it has an exponential component. So this is a transient component, so it will die out with time, and the particular component is the steady state component. Okay, so the total response is the sum of the particular integral plus complementary function. Okay, so the steady state response is the one which has constant amplitude. Right? The amplitude for the steady state is constant. So this is the steady state with constant amplitude. The transient is the one which has the negative exponential term attached to it. So the amplitude goes on decreasing, and the transient portion dies out very quickly. When you start the vibration, the transient portion dies out very quickly. So the solution can be approximated to a particular solution, and this is the equation of the displacement, velocity, and acceleration. And as you can see, the response based on the transient is has some will have some phase lag. Phase lag means what? If the force is applied, okay, immediately it will not show the displacement. The displacement will be after some time. Okay, so that is why there is a lag, a phase lag. That is called as the difference with time difference, or the angular displacement difference. That is called as the phase lag. Now we have replaced this x tilde then phi tilde with x and phi just for our convenience, and we write the equation of displacement, velocity, and acceleration. And what we find is that the displacement vector lags the velocity vector x dot by pi by 2, and the acceleration vector by pi. Okay, so displacement vector is always lagging, and we substituted these values in the governing differential equation, and we what to say, partition the equation into three components on left hand side. One is the inertia component, that is the inertia force. Second is the damping force, and third is the spring force. So this is all on the left hand side. On the right hand side you have the excitation force. So both LHS is equal to RHS, and then we constructed the vector diagram. First we constructed the vector diagram for displacement, velocity, and acceleration. Okay, and we also plotted this excitation force. The equation is F is equal to F0 cos omega t. All right. So the F0 excitation force is at an angular displacement of omega t with respect to the horizontal axis. Displacement vector has a phase and has an angular position of omega t minus phi. Okay. So the difference between this is phi. That is what is the lag. Okay. So it's, see the displacement. It is always lagging the excitation force by phi in this case. All right. Okay. So now we have these three forces: the inertia force, the spring force, and the damping force. Inertia force opposes the acceleration, so the vector is constructed in the opposite direction of the acceleration vector. The spring force opposes the displacement vector, so again it is constructed opposite to the direction of the displacement vector. And the damping force opposes the and the damping force opposes the velocity vector, so again it is constructed in the direction opposite to the direction of the what is it, the velocity. Okay, now based on this all these forces, we constructed a force polygon, and the resultant F0 becomes the resultant of the all these components, that is the inertia component, and so it will balance the inertia component, the spring force vector, and the uh, damping force. Okay, so all these vectors are will be balanced by this F0, okay, or they are equivalent to F0. Correct. Okay, now we also found out the value of F0 by, so this becomes the hypotenuse. So the F0 becomes the hypotenuse. So and it can be found out by using the Pythagoras theorem. So F0 is the square root of those two, and we got the expression for the steady state amplitude. All right, steady state amplitude. So x is nothing but steady state amplitude, and we have readjusted the term so that it is easier to remember, and we converted this equation in terms of r and zeta. And so and if we replace x0 by a term, and we define that is as zero frequency deflection. Okay, so x0 is nothing but zero frequency deflection. So f0 by k in the numerator, we replace it by x0, and x by x0 is nothing but the magnification factor, or it is also called as the amplitude ratio. Right? And the value of the amplitude ratio is 1 square root of 1 minus r square whole square plus 2 zeta r square, and tan phi, the phase lag, is 2 zeta r upon 1 minus r square. All right, so this is what we have completed in the last lecture. All right. So now we will continue. So magnification factor is equal to x by x0, that is equal to 1 upon square root of 1 minus r square whole square plus 2 zeta r whole square. All right. Now let's take a case where zeta is equal to 0. All right. Therefore, if zeta is 0, then the phi is what? Square tan inverse of 2 zeta r upon 1 minus r square. Okay, so if zeta is 0, phi also becomes 0. All right. So now your magnification factor becomes x by x0 is equal to 1 upon 1 minus r square. Okay. Now for r less than 1, the system response, that is xt is equal to x cos omega t, will be in phase with the excitation force. All right, with the excitation. So if I plot these two quantities, so f0 on one and x on the other. Now here there is no phase lag. Okay, we have consider a case where there is no phase lag. So when f0 is maximum, x is also maximum. All right. So this is called as the excitation, the response of the system is in phase with the excitation force. All right. So when does this happen? When r is less than 1. Okay. Now if r is greater than 1, then this numerator, as is denominator, becomes negative. All right. So for r greater than 1, denominator becomes negative. All right. So the response xt becomes minus x cos omega t. All right. So now the response is out of phase with the excitation force. All right. Now again we'll consider the case where the phase lag is 0. So now when f0 is plus f, okay, when amplitude is plus f, then the displacement will be minus x. All right. So in this case, now the phase and the excitation force are out of phase. Sorry, the response is out of phase with the excitation force. All right. So I hope you have understood the difference. Uh, Now, when r is equal to 1, omega by omega n is equal to 1. All right. So in that case, omega is equal to omega n, and that phenomenon is called as resonance. All right. Now in this case, the natural frequency is equal to the forcing frequency. All right. So the magnification factor now becomes, that is equal to 1 upon 1 minus r square. All right. And if you consider the positive, if the that is, this is when r is less than 1, and if r is greater than 1, magnification factor will be written as 1 upon r square minus 1. Okay. Of course, these are conditions. We are assuming that zeta is 0. There is no damping. All right. So what happens at r is equal to 1? The magnification factor goes to infinity. All right. So now if I plot the graph of magnification factor versus the frequency ratio r, at r is equal to 1, this magnification factor curve really goes to infinity. All right. So the response is very high at resonance. Now in this case, see, the graph is constructed of magnification factor versus r, and when r is less than 1, graph is above the axis, above the x-axis. Okay. Now if I use the same equation, that is equal to magnification factor is 1 upon 1 minus r square for r greater than 1. Okay. So the rest of the graph goes below the axis. All right. Now to avoid that, what we are going to do when we are doing the analysis, we are going to, for r greater than 1, we are going to write magnification factor as r square minus 1. So when that happens, your response of magnification factor versus r square will now come above the x-axis, right? And that is how we are going to plot it. Right. So this is when I am using this value. Right. This is when I am using the same for both the cases. That is for r less than 1 and r, that is for r less than 1 and r greater than 1. If I use the same equation, that is 1 upon 1 minus r square, then I get 1 on the other side, upper side, 1 below the axis. But for if I change this to r square minus 1, then I can draw the graph in this manner. Alright. So I hope that is clear. All right. Now, before continuing with the, so next we are going to analyze the uh, this magnification factor, the variation of magnification factor with respect to various design parameters. So before doing that, I would like you to just refresh what or rethink whatever you have just learned till now and answer the first four questions of the quiz. Question 1, 2, 3, 4. Open up your quiz and answer the first four quiz questions. Again, do not submit the form, just make your selection, and so we are going to submit everything at the end of the lecture. And you have 1 minute to complete this. All right, I hope you have completed this. Anyway, you are going to submit it everything at the end. So if you even if you are not completed it, you can complete it by the end of the lecture. All right, so let's continue. All right. So now what we are going to do is study the characteristics of study the characteristics of magnification factor. Right. Study the characteristics of this magnification factor curve. Right. So there is a method to draw this curves. So first we are this is your x-axis. On x-axis you have the frequency ratio, that is r is equal to omega by omega n. On y-axis you have the magnification factor. All right. Now on the x-axis I am going to mark some scale 0.4, 0.8, 1.2. Now see, all of you must have received the what do you say, the PDF of the diagrams. Okay, so I would like you to open that PDF and just try to understand how to construct this diagram, because this is a very popular question in exam, or it is a very important to understand how to construct this curve. Okay, this is 3. Somewhere between 0.8 and 1.2 will be 1. So I'm going to draw vertical line corresponding to r is equal to 1, and just now if you remember we have discussed when r is equal to 1, that corresponds to the resonance. Alright, so that's why this is significant. Okay. Now similarly on the y-axis, again I am going to mark some scale. Let's see, this is 0.4, 0.8, 1.2, 1.6, 2.0, 2.4. All right. So try to understand how to construct these graphs. Okay. 2.8 and so on and so forth. Okay. Now again on we are going to construct a horizontal axis. Okay. So your magnification factor is 1 upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. All right. So when r is equal to 0, when r is equal to 0, your magnification factor is 1, right? Your magnification factor is 1. So all the curves are going to start from this point. So this is 1.0. Right? Now, when r is equal to 1 and zeta is equal to 0, the magnification factor goes to infinity. All right. So this reference curves need to be initially constructed. So I'm going to construct the curve when zeta is 0. Zeta. All right. And similarly construct so this is for zeta is equal to 0. And so if you remember, we are now going to invert this curve. So instead of constructing is below the x-axis, now this will go like this. All right. And it goes to infinity. All right. This is for zeta is equal to 0. All right. Now as you increase the damping, as soon as you start to, so initially this is when zeta is 0. As soon as you start to increase zeta, that is zeta is greater than 0, then you will start to see the peaks. So I'm just going to construct 1, and again this goes here. Right. Now there is some critical value. Okay, now if I keep on increasing zeta, then the peaks are going to appear. Right. Now at a certain particular value of zeta, this peak disappear. Okay, so we will discuss when this happens, but try to understand how to construct these curves. Okay, so this is zeta is equal to 0. This is zeta, suppose 0.3, and this is suppose 0.5. Okay. Now these are the curves. Say suppose this is zeta is 1.5. So for very high values of zeta, there are no peaks that you observe. Okay. So this is for zeta is equal to 0.2 and so on and so forth. All right. So this is how you have to construct the frequency response with respect versus magnification factor. Now we will see what are the critical features of this graph. It's okay. So after you construct the graph, so this is how it appears. Okay. Now we will see what are these key features of this graph. Okay. And what is the specific behavior of this graph. Right. So one by one we will see the features. Okay. So first point, for an undamped system, that is for an undamped system, all of you please pay attention to this all this discussion. There is going to be quiz at the end of this discussion. Okay, so for an undamped system, zeta is equal to 0. So when zeta is equal to 0, magnification factor goes to infinity, right, as r tends to 1. All right, so near resonance, this magnification factor tends to infinity as r tends to this value. Okay, so when this in the near resonance values of the frequency ratio in the regions at or near resonance, the magnification factor for an undamped system or as for a low damping, this response goes to infinity. Okay. Now, as soon as any amount of damping is introduced, that is when zeta is greater than 0, the magnification factor for the magnification factor at or near resonance start to reduce. All right. Okay. So what does that mean? See, as soon as now here magnification factor when zeta is 0, it goes to infinity. But as soon as you start to introduce the damping, then this magnification factor near the at or near resonance start to decrease. All right, so this value start to decrease. Okay, for any specified value of r, a higher damping reduces magnification factor. Okay. So for if you see any of this value of for r, as soon as the damping is introduced, then the magnification factor for any given value of r will be less compared to the undamped one. Okay. Now, suppose there are two magnification factor curves and zeta 2 for the second curve is greater than zeta 1, then magnification factor of the second curve will be less than magnification factor for curve 1. Okay, for all values of r. So if you see, when zeta is increased, the magnification factor of this second one is, see, if this is 1, see if this is zeta 1 and if it is zeta 2, okay, zeta 2 is greater than zeta 1, but magnification factor of all the points on the curves is be less than magnification factor for all the points on curve 1. All right. Any questions so far? Can I continue?
Yes.
All right. Please pay attention to all the discussion because you know there is going to be quiz on this. So when r is equal to 0, magnification factor is 1. That is called as the degenerate case of a constant force. What does that mean? See, it means that basically when R is equal to 0 means frequency ratio is 0. Means basically what it means is that the system is at rest. Okay. So this is a degenerate case of constant force. Okay. For zeta is equal to 0, R is equal to 0, the derivative of magnification factor with respect to R will be 0, because then magnification factor becomes constant. Okay. Reduction in magnification factor is significant in presence of damping, especially at or near resonance. Alright. So if you see the region which is near to resonance, that is when R is equal to 1, see when zeta was 0, the magnification factor was infinity. Okay. As soon as you introduce some amount of damping, the magnification factor reduces. So in this case, it is somewhere in between 1.6 and 2.0, so maybe something like 1.85 or something like that. All right. So from infinity, when zeta is 0, so when zeta is 0, magnification factor was infinity. But as soon as some damping is introduced, then magnification factor reduces to a value something like 1.85. Okay. The amplitude, next point, is the amplitude of forced vibration tends to 0 as the forcing frequency increases. Right? So in other words, what does it mean? Magnification factor tends to 0 as R tends to infinity. That you can see from this region in the graph. Okay. As R tends to infinity, the magnification factor tends to 0. All right. So you can see in this portion of the graph, the magnification factor is very low. Okay. So how can you deduce that mathematically? Say suppose I can write the equation in the form of divide numerator and denominator by r square, and I can get 1 upon r square at the numerator, and at the numerator it will be 1 upon r square whole square plus 2 zeta by r whole square. All right. So this is your equation for magnification factor, right? So this is your magnification factor, and if I apply a limit where r tends to infinity, then what will happen to the magnification factor? That is x by x0, this will tend to 0, right? So when magnification factor tends to 0, x0 is constant, so the amplitude of the force vibration will also tend to 0. All right? So this is the summary of all the points we discussed just now. All right. Any questions? All right. If you have any questions, you should ask now itself. Once the quiz is started, you cannot ask any doubts and questions.
Sir, there would be no curve of zeta equals to 0.
No curve of there is a curve for
zeta
zeta equal
equals
to
to
0,
0.
so this will be something like this. So in this diagram it is not constructed, so zeta is equal to 0, it will really go to this infinity. Alright, so it will be something like this. We have constructed that separately while we discussed the case earlier, right? So here it is not shown. So this will be
But sir,
some
if r is less than 1, so there would be some magnification factor na, for zeta equals to 0.
r is less than 1. No, this is for at resonance condition r is equal to 1. See,
Okay,
magnification
sir.
factor. This is specific condition that is at or near resonance. Any other questions before we go
Sir,
on to
at
the
zeta is equal to zero point 0.3, when
huh?
the magnification factor is the maximum,
Huh?
then the derivative of the magnification factor with respect to frequency ratio would also be zero, na?
Yes, right. That part we have not like discussed, but we are going to discuss it in the next step. But that is correct. And these are the peak values, right? This is the maxima. So at maxima, if you take a derivative, and so magnification factor is function of in this case frequency ratio, right? So derivative of magnification factor with respect to the frequency ratio at r at peak will be equal to 0. Now that frequency ratio is not, all right. So now since you have brought up this point, it is important to note that that frequency ratio is not equal to the resonance value. All right. This is
Can you
r is
repeat?
not, see, when m magnification factor is function of frequency ratio, right? So at for finding the maxima, if I take a derivative with respect to r for some particular value of r, this derivative will become 0 and the magnification factor will become, the magnification factor reaches the peak value. But this peak value is not reached when r is equal to 1. Okay, it is reached at a point slightly before r equal to 1.
Okay, okay.
All right. Any other questions?
So can you
This
explain the
slide,
amplitude
which one?
once more?
This
The
amplitude,
last one, amplitude.
see
Yeah.
what is said, the amplitude of the force vibration becomes smaller with increasing value of forcing frequency. Okay, or in other words, magnification factor tends to 0 as frequency ratio tends to 0, tends to infinity. See, what is r frequency ratio? Omega by omega n. What is omega in the numerator? That is the forcing frequency. All right. So when this r will reach infinity, when this ratio tends to infinity, right? Because omega n is constant, natural frequency is constant. So in other word, when the forcing frequency reaches infinity, then the magnification factor tends to 0. That you can see from this graph, right? So when magnification factor tends to 0, that means in other words, x by x0 tends to 0, right? So again x is constant. So in other word, what does it mean? X tends to 0. And what is x? X is nothing but the amplitude of forced vibration. That is what it means. Any
Yes.
other questions? All right. I think this was a good discussion. Now just no, this is just for you to refresh your whatever we have discussed. These are the some of the questions from now answer from 5 to 12. Again, I will give you like say 2 to 3 minutes. all of you also on your pen have a pen and paper handy. Okay, so on that pen and paper, just make a record of your whatever responses you have chosen. Okay, so for example, for question number 1, you have chosen true, just write it on a piece of paper. Question 1 is 2, question 2 is for whatever it is. All right, so till 12 I want you to maintain from question 1 to question 12 whatever answers you have recorded, because what might happen, see, only 20 minutes are remaining. It might happen that there are 22 questions, so we will not be able to maybe finish all the content for the 22 questions. So in that case, I will reduce the length of the quiz. So I will delete some of the questions, and then you have to again just say make the selection and submit it. Is that clear to all what I am asking you to do?
Okay, sir.
So all of you on a piece of paper maintain a record of whatever response you have chosen. So right now it is for question 1 to question 12. Record your responses on piece of paper. Okay, do not forget this. Please make sure you do this, because there are 22 questions in the quiz I have designed for today, but maybe we will be able to finish maybe 16 or few. If you are able to finish all of them, then that is good enough. I will give you 1 more minute. Even if you don't complete it right now, you can just put a hold on it and complete whatever is remaining at the end of the lecture. All right, so let's move on now. If you are alternatively, what you can do, if you want to solve the quiz, just take a snapshot of it or do a print screen and just save it somewhere. Okay, so we'll continue with the discussion now. Now we'll come to the maxima part, which we have just discussed before the quiz. So for a damped system, the magnification factor is 1 upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so let's call this sign under this whole sign a term under the square root as d. All right, so derivative of magnification factor with respect to time, that will be minus half into d raised to minus 3 by 2 into derivative of denominator with respect the d term with respect to r. Okay, and this will be equal to 0. Okay, and so this term is not going to be 0, so obviously the derivative is going to be 0. So I can equate d by dr of 1 minus r square whole square plus 2 zeta r whole square is equal to 0, and you can take the derivative. So it is 2 into 1 minus r square into minus 2r plus 2 into 2 zeta r into 2 zeta is equal to 0, and when I simplify this and when I find r square, r square is equal to 1 minus 2 zeta square, or r is equal to square root of 1 minus 2 zeta square. And so this is when the magnification factor is maximum, or the peak is reached. So this frequency ratio is called as RP, that is the peak frequency ratio. All right. Okay. So we have derived the expression for peak frequency ratio. Okay. Now we'll continue our discussion based on this expression. Okay, so we are going to use this expression and continue our discussion. So for damping factor between all right, you will observe the peaks in magnification factor curve can be observed. Now where did I get this root 2? The peak magnification factor is square root of 1 minus 2 zeta square. Okay, so this assuming the limiting value is 0, right? So when I put this, I get zeta is equal to 1 by root. All right, so the magnification factor, the damping ratio should be between 0 to 1 by root 2. Okay, only when that happens, this term will be RP will be greater than or equal to 0. All right. So as long as RP is greater than or equal to 0, or this term under the root is greater than 0, you will see these peaks in all these magnification factor curves. So for example, this is 1, this is 2, this is 3, this is 4. So in the shown figure, till 1 to 4 you are seeing peaks. But when you go to the fifth curve, that is corresponding to zeta is equal to 1.0, then you do not see the peaks. Okay, for this is an example. So what happens to this value when I put zeta is equal to 1? Okay, so this becomes 1 minus 2 into 1 square. So that is square root of minus 1, right? So when zeta is greater than 1 by root 2, then this term becomes complex. The frequency ratio, the peak frequency ratio term becomes complex. As soon as the peak frequency ratio terms starts to become complex, the peaks disappear and the curve, the magnification factor curve, decreases monotonically. All right. So as you can see, all these curves over here in the lower portion, they decrease monotonically. There is no peak observed for such curves. Okay. Now one more thing. So this is one important key feature of these curves. So now second features. See, if you see these peaks, just see, if you see these peak values, as zeta increases, the peaks shift to left. All right. So this is a trend is observed where the shift is happening on the left hand side. So why does that happen? The RP value is nothing but 1 minus 2 zeta square. Okay. So as you increase this value, as zeta increases, Rp goes on decreasing. Okay, so this peak values goes on decreasing. So this curve, the peaks of the curve, they shift to the left. Okay, so this is also one of the very important key characteristic features of this curve. Okay, so I have summarized all the points uh, on the slide. Again, go through them, and if you have any questions, please ask. Now this Rp is called as the peak frequency ratio. Everything is clear? No questions? Can I move? All right, I think I can go to the next slide now. All right, now few more points are to be discussed. So when R is equal to square root of 1 minus 2 zeta square, then the x by x0 is maximum, and this comes out to be 1 upon 2 zeta upon square root of 1 minus zeta square. Okay. Now this equation can be used in experimental determination of zeta. Okay. So in a vibration test, if the maximum amplitude of response is measured, so if you can measure x max, okay, x0 you already know, initial displacement, and so if you know x max, if you can measure x max, then you can find out zeta. Okay, so that is how you can experimentally determine the value of zeta. Okay, now when r is equal to 1, x by x0, when omega is equal to omega n is equal to 1 upon 2 times zeta. Right? Now the amplitude corresponding to the peak value of magnification factor is called as peak amplitude, and the corresponding frequency is called as peak frequency. Alright. Okay. Alright. Now last 5 minutes are remaining. So I think you are required to solve only up till 16. Question number 16. So I am giving you the remaining 5 minutes of the lecture for completing the quiz. Okay, so these are the questions.
Sir, could you go just back to the last slide for just 1 minute?
All right. So let me just take a snapshot of the questions, and I have to delete the remaining questions. So otherwise, you will not be able to. All of you have made a note of your responses, right? I have told you to do that. Just I will just stop showing for a minute. All right. Okay. So now you can submit answer all the 16 questions, and then you can submit the quiz. In the meanwhile, I will just download the attendance. You can answer the quiz, all the 16 questions. You have till 11:10, that is the end of the lecture, to complete this quiz. How are you trying to see the responses? Because I'm posting all the responses, the students are saying that they are not able to see the responses. So how do you see the responses? I have also enabled what do you say, a receipt that is to be sent, that will be sent to you by email. Have you checked your email? Are you getting the receipts?
So, sir, we are not getting the responses from me.
No, I mean the responses you should be able to see after you click the stop sharing. Okay, I have enabled send email receipt to correspondent. So I think you should get the receipt from at least from today once you submit the quiz.
Sir, questions.
Just a minute. Just. All right. Let's complete the quiz. Only 1 minute is remaining. After that, the response will be closed.
Sir, the questions which are after question number 16 are also compulsory, so we won't be able to
No, no,
submit all
just
of it.
refresh. No, no, just you don't have to submit it. I have deleted. You are just seeing it on your screen. Okay, if you just answer till 16 and submit it, no, the form should get submitted. If not, refresh the screen and just that's why I told you to make a note of all the answers till question number 16. Okay. So before refreshing, see all of you please pay attention. If you just submit the form, if you are not able to submit the form, okay, just do a refresh on the screen and again re-enter the answers.
Okay, sir, thank you.
And before doing the refresh, make a note of all the 16 questions, answers of all the 16 questions that you have attempted. Otherwise, you will not know what is the answer you have chosen. Okay, I am not seeing any. Okay, I have seen 31 responses. All right, time is up. All of you submit it. See, it is already 1 minute past. Okay, submit your responses. I am closing the responses.
Sir, 1 minute it is reloaded. You have to
Huh?
again put the answers.
But why did you attempt to submit it? Why did you
Yes, I have
reload it?
submitted, but
Okay,
it
okay,
shows
just
the
answer
all
it
others are
quickly.
compulsory, so I
Yes,
Answer
sir.
it.
have.
Yes, sir.
Answer it quickly. I am keeping it open for 1 more minute. All right, done. Okay, I am closing the response now. I hope everybody is done. I am closing the response. All right, the responses are closed now. Have you received? Okay, now those students are online. Have you received the, what do you say, receipt in your email? Hello.
No, sir.
You in your mic? Which email are you seeing? You have to see your Microsoft
Sir,
Teams.
actually, we need to log in our email ID, then only we will see.
Ah, so you are not logging in with your email ID.
No, sir, not yet.
Sir, where can
Huh?
Microsoft का email ID?
Microsoft email ID, it should be there in your account. When you see the Teams account, na, in that you should see it. Anyways, if you are figure that out, that's all for today's lecture. I will post. I'm just posting the scores. Those who are able to see. Oh, so you are not logging in with your IDs. That's why you are not able to see the scores. You need to log in with your IDs. Only then you will see the scores.
Sir, we have logged in with our IDs.
Okay, now I'm posting. Who is that? Who was that?
Swami Shriram.
Okay, now I'm posting the scores.
Yes, sir. Now we can see.
Oh, okay, I'm ending the lecture now. If you have
Sir,
any issues, huh?
Very questions for term test.
Whatever has been taught, nothing special.
Sir, derivations.
Sir, who's
Derivation.
the answers?
What's the?